Give it a moment to warm up. So here we go. This is just a little relaxed session poking around in the Studio GUI to run some standard LuaJIT benchmarks in RaptorJIT, get some profiler and JIT dump data as a result, and poke around and have a look. So we got about half a dozen benchmarks that we're going to run straight off GitHub. Download a tarball containing them. Click the little go button, and now Studio is downloading the benchmarks, running them. Going to get some cold data out at the end, so the Lua process will be completely finished, but it will produce a JIT dump and some profiler data, and we see what's in there and what we can say. Here, let me just widen this a bit. So here we have on the left side we have our kind of input area where I'm telling Studio what to do. I told it to please fetch a tarball and run the Lua code that it finds inside. On the right hand side we have the result of doing that. So it's a RaptorJIT process, logs from a RaptorJIT process. The default thing that it shows is the profiler datasets. So inside the program I have a few calls to create named profiles. I run here half a dozen benchmarks, and each one it just has its own profiler data so that it doesn't get mixed around. So everything runs inside the same Lua VM, and all the kind of generated machine code and everything is all mixed in together, but then we untangle that using the profiler. So then we can pick a benchmark and see just the code that was halt in that particular benchmark without getting distracted by everything else. So I think the nicest thing to do now would be to take a really kind of high-level look at each one and see what we can tell before we dive into any code. So here we got the profiler datasets. We have a profile called Meteor, one called MD5, Series, Euler, Array 3D, and Coroutine Ring. And for each of these profiles, we can see a little bit of information. We see the number of samples that the profiler took while running that benchmark. The samples are taken in a really simple way. This is an iTimer running at a 1 millisecond interval. So basically 491 samples in the Meteor benchmark kind of more or less means that we spend about 491 milliseconds running that benchmark. So we can get a little bit of just a feel for how long things took there, the relative speed of each of the benchmarks. We can also see the proportion of time that each benchmark spent in each state. So the Meteor benchmark spent 6.7% of its time running machine code. Machine code means either code that was generated by the JIT compiler or foreign functions that were called through the JIT. It spent 92.9% of its time in the virtual machine, which in this case probably means the bytecode interpreter, so running code that was not JITted. It also includes kind of runtime system calls for table creation, table lookups, and that kind of thing. And it spent a very tiny amount of time in the garbage collector. So just by looking at that row, it kind of looks like something is fishy here. It looks like that the benchmark was not able to JIT successfully, and that's something we can take a look at. If we take a look then at the MD5 benchmark, it's a bit of a different story. It's spent 99.7% of its time in machine code, which is more like what we want to see generally. If you're doing kind of system programming stuff anyway, you generally expect to be spending almost all of your time running in machine code generated by the JIT, which looks nice there. Series benchmark, it can't be better. It spent 100% of its time in the JITted machine code. Euler benchmark, a lot. Array benchmark, a lot. The coroutine benchmark spent about half of its time in machine code and the other half in the virtual machine. It will be interesting to see if we can figure out what the difference is there. Coroutines, it certainly sounds like something that's going to be making a lot of calls into the runtime system to switch between coroutines, so it maybe makes sense if we spend part of our time running JIT machine code for the Lua, and then the other part where the Lua calls into the virtual machine to swap out the coroutines. So let's take a little look inside. Okay, so the Meteor one, it's a bit special because it's running mostly interpreted. So something that is weak, but there anyway in this UI is to look for the reasons that things failed to JIT. I would like to have this really nicely cross-referenced. I don't have it that way yet, but if we look in the Events tab here, we get a list of all of the events that were logged during the execution. So we see a trace stop is when a trace was made successfully. A new prototype was when a new bytecode function was defined. That's when we load code. Lexing event is when the lexer sees some source code. So something that I recently added is to log all of the source code that comes in so that we can cross-reference that in this UI. But the cross-referencing isn't there yet, so it's invisible. It's present. And the aborts in this case, what we would be interested in. So this benchmark has been running a lot interpreted. We expect to find some aborts to tell us why did the attempts to trace fail. But the trick is going to be to find the right ones. So let's do it a little bit primitively now and just scroll down until we see, which benchmark was it? Meteor benchmark. So we want to scroll down until we see basically the Meteor source code getting loaded. And we know it was the first benchmark, so we don't necessarily know that. Here we go. A bunch of functions defined from meteor.lua. This looks promising. So we see some successful traces, trace stop, and here's one that failed, trace abort. Let's have a look at that. We get a little bit of information about the abort. We see the source code line where it started. We see the source code line where it ended, which is probably where the problem was, but reached a point where it said, I can't compile this successfully. We see that it recorded 77 bytecodes, and we see the reason was a call unroll limit reached. Okay, so somehow it was trying to unroll a lot of function calls, and it reached a point where it had done too many and it wasn't willing to do any more. Then we have this final flag at the bottom, which is kind of nice. This tells us did the JIT treat this as just a glitch that's going to be tried again later, or did it consider this to be final, that we shouldn't do any more tracing? So this was not final, so we don't have to necessarily worry about that. It's normal for the JIT to try a few things that don't work out and then find something better, but it's problematic if it persists and eventually it blacklists some code by saying that it was a final stop. So if we just click another couple of aborts, that one's basically the same. Of course, in the future this will be much nicer, and I'll highlight all of the fatal final traces and everything, but at the moment it's just a bit of a clickety-click around. Here's one that happened for a different reason. It's a not yet implemented bytecode. You can hop over the bytecode list and see it was a call to the next iterator function, which apparently doesn't compile. So we can see a little bit of what's going on. We can follow along, keep looking at the aborts until we find something a little more. And none of those ones were final. Interesting. So I don't know why, for this particular problem, why it never managed to create a trace. It certainly has the look that it managed to create a bunch of traces. None of the aborts seem to be final. So I don't know. I have to improve the tooling in that case. I guess that the joy of this is to highlight a lot of things that need to be the next things to fix for the to-do list. Okay, don't know. Something is wrong with the Meteor benchmark. It runs really slow. It runs mostly interpreted anyway. MD5, let's just hop into. So this is running in machine codes. If I select this profile, now what it shows me here, get that one over there out of the way. So so I select this profile for the MD5 benchmark, and now it's showing me where the root traces were. So that's some source code location that was executed often enough that it became hot, and the JIT said, okay, this is a good place to start compiling code. So the candidates for getting hot are function heads, entry to a function, or loops, and loops get hotter more quickly. So I'm going to select, well, I can see a little bit of information about this anyway. So in the set of traces, the tree of traces that are rooted at this source code line, MD5.lua line 127, there were all 707 samples there, and in this collection we have 2 root traces and 4 side traces. So if we select that, then we see a little bit more information down here. So this should give us a little bit of more insight into the way that the compiler did things. So there's one root trace there and another root trace there, and then we see there were some side traces. So it started root trace number 2 at a certain point, on line 131, which I don't have neatly cross-referenced here. We use our imagination. When I got to line 131, then something happened that it couldn't stay on the root trace. It needed to exit to a side trace, and it did so. And then from that side trace, there was a further exit at line 137, where it hopped off again. And the profiler data here is actually pretty useful to look at. So looking at the number of samples, the hottest trace is actually this side trace. So we have a root trace here, which was reasonably hot, 186 samples, and this is a looping trace. So this is a trace where loop optimization is kicked in. The trace, or the trace is trying to loop back to itself. But what happened very, very frequently, we see here, is that it didn't manage to complete a loop because it needed to take an exit and go off to a side trace. So this is a case, something I just blogged about, where the loop optimization is sometimes really great and has a big benefit, but it's not kicking in here. We can see because we see that the side trace is hotter than the root trace. We're not staying on trace on the root trace all that much. So this is a case where it's there's modest benefit presumably to the loop optimization. There's a little sound coming from down there, which is my little assistant. Just introducing you, Joey. Okay, so just looking at this, what we can see just at this high level view is that it compiles to a little. So there's a little bit of diversity in the way that it executes in either the branching or the types of the code, and that this really this hurts a bit. So the loop optimization wasn't able to help very much there. So probably if loop optimization worked better, we would get a really big benefit on this benchmark by not having such a hot side trace there. Just taking a look at the next benchmark. Here we have again a single source code location where everything starts, which is series.lua line 5. There we got all 2,000 and so samples. We have 3 root traces and 3 side traces. And this is interesting. So here we have a root trace here, which got about half of the samples and runs in 100% machine code. Then we have 2 side traces. So these are exits from the root trace that were taken frequently enough that the JIT decided to make a side trace out of them, but were not executed frequently enough to actually show up in the profile. So from a performance point of view, these are completely irrelevant. So these are totally harmless side traces. So when we see the second root trace down here, trace number 26, has the other half of the samples pretty much. There are a couple of samples in these traces over here, but basically all the time is spent in trace 25 here, which is a looping trace that's 100% machine code, which is great, and trace 26 here, which is a looping 100% machine code trace, which is great. So just at a glance, this looks like it was at least compiled very, very effectively. The optimizations that you want to kick in did kick in, and they work very well. If these side traces had been hot, then it would be like in the MD5 benchmark. We'd say, okay, well, we seem to have a lot of branchiness here that's kind of swimming against the current of a tracing JIT that wants to stay on trace, keep running in a straight line. But that's not what we see here on the series benchmark. It looks to have compiled really nicely, which is great. How about the Euler benchmark? Here we have 2 root traces, 5 side traces. Again, everything starting from a single source line, line 11. So this one is a little spread out. So we have again 2 root traces. One here that has some side traces. Another one down here that has 1 side trace. The 2 root traces here is reasonably hot, 179 samples. This one is also reasonably hot, 200 samples. This side trace was the hottest with 264. So this is kind of like something between the situation of the last 2 that we looked at, right? So the majority of the time was spent between the 2 root traces, only one of which is looping. This one doesn't loop, and then some all time was spent over there. So it looks kind of like a reasonably successfully compiled code, kind of close to some of the sweet spots of the JIT. But if we wanted to optimize this, we'd probably want to have a good look at see why was it that on Euler line 12, we branch off very frequently to a side trace. And could we somehow keep this on trace? Could we somehow have a single trace that handles both of those cases? I don't know. We'll have to pull in the source code cross-referencing support so that we could click there and look at the code and see what the high-level reason is that it makes the branch. The array benchmark. There we go. The array benchmark, we have one sample from the MD5 benchmark here, which is kind of an interesting thing actually. So traces can span kind of arbitrary points. So it's always possible that a trace that originated in one part of the program continues into another part. And so here we managed to grab one sample with the profiler while we were switching from one to the next. So we can just ignore that pretty much. So again, we have the one source line that starts it all off, array 3D line 55, with one root trace and 3 side traces. So we have a root trace that again is looping. It's running 100% machine code and has got about half of the samples, and then we have a side trace down here that has basically the other half of the samples is also running machine code. So I guess this is becoming a bit of a common pattern where we have a little network of traces, and some of the time is spent on a root, probably getting the benefit of loop optimization, and other time is being spent on side traces. And this is just the reality when you have kind of branchy code or code that deals with a lot of different data types. The way a tracing JIT will work is that for every different way that you can execute the loop in terms of branches and types, it will generate a separate block of machine code representing exactly that scenario. And here we have 4 of them. This one executed quite a lot, and it was the root, so it was eligible for some more optimizations. This one over here executed also quite a lot. It's a side trace that couldn't get as many optimizations done, which is a pity. And then we have these other 2 side traces here, which are just completely irrelevant from a performance perspective. This one didn't get any samples. This one got 1 sample. And actually a nice thing about doing everything through the profiler is if you were just reading like a machine code dump or something, you wouldn't know where to look. You might be looking very carefully at the code for this trace, which is completely irrelevant, or this one. You really think it's totally crucial to do everything through the profiler. Otherwise, you're just gonna not be looking in the right places, not looking at the right things. I think we can kind of wrap it up shortly. Let's just have a little zoom in on some of the code and see what we can see. So if this one starts at array 3D line 55, we see all of the bytecodes that it executes running down, and we can see the intermediate code over there. There's a lot going on, and if we zoom in, we can kind of to the extent that we want to, we can see what the code is doing. But there's something interesting actually about the shape of this code. So here we have a bunch of intermediate instructions here, and they're arranged in a graph, and the graph is showing basically the data dependencies. So if we go in close, we see that this instruction here, the multiplication, takes one of its input from a hash table load there, and another of its inputs from something else over there. And the shape of this graph actually tells us a little bit about the dependency. So this is very wide, right? It runs very wide, and it's not all that deep. And this is kind of relevant when you think about the way the CPU is going to execute the code. These IR instructions, like we see here, each intermediate representation instruction corresponds pretty closely to some machine code, and the edges between them with the dependencies are more or less when one instruction writes something into a register and another instruction accesses that register. So these are the data dependencies that the CPU will see. So on an out-of-order CPU, like an Intel CPU that can be executing 8 different micro-ops at the same time, the fact that this is very wide rather than very tall is significant. So the width corresponds to kind of how much work has got to get shoved through the processor, and it can be done in parallel. Whereas the height is kind of about the long chains of dependencies. So there's a kind of a sweet spot. If you have a very tall If you have a very tall IR graph or a very tall kind of dependency graph, then that's going to take a very long time because the CPU has to do this before it can do this, before it can do this, before it can do this, before it can do this. So you might actually have a lot of idleness sitting there if everything is depending on something else. And then when you go out to memory, the CPU has nothing to do until the result comes back. Whereas if you have something very broad, like what we have here, then you're probably not that sensitive to latency. So if you would have a cache miss or something like that, or a branch misprediction in here, it very well might not matter because what the CPU is, because the CPU is not really sensitive to latency here. It could be more of a throughput kind of thing. It's just got a lot of guards. If you look at this stuff happening over to the side up here, it's a lot of guards. It's loading something and loading a hash table, checking that it's the same hash table that we saw when we generated the machine code, checking that it hasn't been resized, all this kind of thing. And that stuff can be massively parallelized. So it will be an interesting thing for the future, actually, to be able to get a little bit of a view of the CPU performance counters and see how busy is it when you're executing these kind of things. It's very important to know when the processor is executing this trace, is it mostly actually really busy in the back end, executing all of the instructions, doing all the checks, or is it mostly sitting waiting for something to happen, like waiting for a memory access to come back so that it can unstick some instructions. So that's a topic for the future. I think this Intel ptrace hardware feature will be the way to go for that, where you can get some very precise information about when branches are taken, this kind of thing. Anyway, I'm going to stop talking now. Thank you very much for playing along. Bye-bye.